We now come to the heart of the matter of the direction of change. And the heart of the matter is the second law of thermodynamics. A great deal has been written about this law. It's been quoted as the sine qua non of scientific enlightenment, rather as Shakespeare and Beethoven might be quoted to represent the arts. Whilst the position of Shakespeare and Beethoven in our common culture might be said to be secure, the position of the second law of thermodynamics is perhaps less assured. An ex-vice-chancellor of Oxford University recently said, "Thermodynamics, I don't even know what it is." And one detected a note of satisfaction in the pronouncement. And yet, it's an idea of great significance and beauty, and one which affects every aspect of our lives. It's true that some specialized knowledge is required, perhaps a little mathematics, to interpret the law fully. But a specialized training is necessary to interpret Beethoven fully. The real question to us is, can we understand the law well enough to derive pleasure and satisfaction from it? And I hope that you will agree with me that this is possible. In fact, the essential idea of the law has already been stated. It isn't a difficult idea. It's the idea of increasing disorder, that the randomness, chaos, disorder of the universe is always increasing. Now, a full statement of the law can be made in many ways, and to some extent it's a matter of personal preference. Just so as to treat the subject fairly, I shall state it in at least 4 ways, but the one I prefer is the first one, which I've written on the board as neatly as I can. Every system, if left to itself, will, on the average, change towards a condition of maximum probability. That's a full statement of the second law. 1 or 2 things about it are worth noting. First of all, the word system. This is just the thing we're interested in, the machine, the substance. Whatever we happen to be interested in, we call the system. Probability. We talked about that. Probability is just a measured as the number of ways in which the system, which we've defined, can arise. And finally, the words "on the average," which don't appear in all statements of the second law, but should, because the law is a statistical law. The earlier statements didn't deal with it as a statistical law. It is statistical, and deviations from the second law of thermodynamics are possible. It's only true on the average. The Brownian motion, which we saw, shows every time the little Brownian particle moves a departure from the second law. But on the average, the second law is obeyed. It's a statistical law. Now, we saw how entropy was related to probability by the equation S equals K log P. And therefore, if the probability is going to a maximum, as it does in the statement which I've just written, so the entropy should follow it. And so a second statement which we can use is the one I've written here. In any spontaneous process, the total entropy increases. That follows from the S equals K log P. Now, the word total here is very important. We must remember to include everything which takes part in the change, otherwise we shall get our sums wrong. If necessary, the whole universe, anything involved in the change. In fact, this inclusion of the whole universe is quite a good way to do it, and Clausius very succinctly expressed both the first and second laws of die Entropy strebt einem Maximum zu. The energy of the world is constant, the entropy tends to a maximum. Now, I can express that statement mathematically very simply indeed. This, if you like, is a third way or fourth way of expressing now both laws of thermodynamics. First of all, the first law says that the increase in energy of the universe equals naught. There's the first law of thermodynamics, and the second law says that the increase in entropy of the universe is equal to or greater than naught. We said that the entropy of the universe is always increasing. That means it's greater than naught. Well, it can be just greater than naught. It can be equal to naught. It mustn't decrease. So those are two ways of expressing the first and second laws. We shall meet others. The second law is a strange law. Nothing is conserved, nothing adds up. Most laws of science are concerned with the conservation of something, the conservation of mass, the conservation of energy, or something like this. This second law just doesn't add up. It says something increases all the time. But we shall find that it's a quantitative, useful law nevertheless. Whilst we're at it, I might refer to the other law of thermodynamics, the third law, because it's quite quickly disposed of, for the moment anyway. The third law is one which deals with the absolute value of the disorder or entropy. The third law says that the entropy of a perfectly crystalline substance, perfectly ordered crystalline substance at the absolute zero may be taken as zero. And if we want to write it, we can write it as S at the absolute zero equals zero. But I'll dot that round because you must remember that that is, has the restrictions which I mentioned in the full sentence, which I just spoke. Well, there are the three laws of thermodynamics, very simply expressed. Now let us look at some examples of spontaneous changes and see how they are accounted for in terms of the second law of thermodynamics. We'll take the simplest first and look at changes where only the entropy changes. Now, one, perhaps the simplest of all of these, is the expansion of a gas into a vacuum. I have in one of these bulbs some bromine, and in the other I have a vacuum. And if I open the tap between these two, you will see spontaneously the bromine rush from one to the other. Now that is the simplest change we can have, perhaps, because all that happens is a change in entropy. In this case, the expansion into a vacuum, nothing else is involved. There's no energy change, there's no temperature change, there's no change except entropy. So without the entropy concept, that would have been difficult to understand and difficult to account for. True, if it had to push against something and do some work, then there would have been heat and energy changes. For, as you know, if you let the air out of the tire of your car, the valve gets cold as the air does work against, pushing against the outside air as it expands. But this is not true if it expands into a vacuum. Another very similar and rather interesting process, which is just an entropy, is explained in terms of entropy changes, is the spontaneous contraction of a bit of rubber band. This, strangely enough, doesn't involve energy. Hardly at all. The process is explained almost entirely in entropy terms. What happens is just like the expansion of a gas. That is just like the expansion of a gas into a vacuum. The system is taking up a position of greater freedom and more higher entropy. You see, it's as if we're pulling the molecules of rubber apart like this, and what they want to do is acquire thermal motion like this, entropy, just like an expanded gas. And when we hold them apart, they have the same energy, but they can't take up this freedom, this higher entropy, and they do this as soon as we release them. So it's just like, although it's a contraction, it's just like the expansion of a gas, and involves an increase in entropy. And just as when we allow a gas to do work when it expands and it cools, it's the same here. If you let this contract like this and do a little work as it does so, you feel it get cold as it does so if you put it against your forehead. Well, that's a simple entropy increase process. And there are many, many other examples. Now let's consider another type of spontaneous process, which is a little different. If we put a pan on a hot stove, the heat flows from the stove to the pan and never the other way around if the pan is cold. Heat always flows from the hot to the cold. Now this follows immediately from our statement of the second law, because we know that in a heat flow, we know that the entropy is equal to Q, the heat absorbed over the temperature. And so that if we transfer an amount of heat Q from a hot to a cold body, temperature hot and temperature cold, I'll use as the symbols, then the entropy change will be Q over T cold minus Q over T hot. Now, T hot is greater than T cold, so this is less than this, so the whole thing is positive. That means delta S is greater than naught, and so it's a spontaneous process. If I'd made it flow the other way around, this would be less than naught. The entropy, total entropy, would decrease instead of increasing, and this would be contrary to the second law of thermodynamics. So this follows from the second law, but it is also a statement of the second law, which is very often used, that heat cannot of itself pass from a colder to a warmer body. This is one of the earliest statements of the second law of thermodynamics, which was developed in this way from the study of heat, as I've explained before, not from the study of statistical processes, molecules, and probabilities. It's useful, but it's less general. It's rather abstruse. It's not so fundamental and not so interesting as the statistical approach which we've used, and I think it is the use of this historical approach in textbooks and in generally developing the science of thermodynamics which makes it so terrifying to many people. It is considered to be a really rather abstruse and difficult subject, and this, I think, is to a large extent due to the fact that it's introduced through heat and heat engines and so forth, instead of via the rather obvious to most people statistical implications which it has. Certainly I find it more interesting from a statistical point of view. Well, we've seen then a number of spontaneous changes which we can account for. Now let me show you another one. Here I have a solution of sodium thiosulfate, photographer's hypo, and it's an oversaturated solution, and I'm going to pour it into this crystallizing dish, and now just to encourage it a little, I'll drop in a few tiny seed crystals by rubbing a couple of hypo crystals together like this. And now look what's happening. As I do that, you see those little crystals which I've dropped in growing spontaneously, shooting out stars. See these star crystals which are being shot out from here. Beautiful regular crystals shooting out in all directions. This is order growing in front of our eyes from disorder. Something has gone wrong with the second law of thermodynamics? No, something has gone wrong with the way we're applying it. We're thinking only in terms of these crystals themselves, where surely and certainly, there's no doubt about it, the order is increasing. But the secret to it lies in, is revealed immediately I touch this solution. It's warm, it's really quite warm. Heat is being given out in this process. And there, in that heat which is being liberated, we have the compensating process of entropy production in the other part of the universe. The thing is, we forgot the rest of the universe. We didn't consider the total entropy. Let me show you what I mean. Let me bring this tube over here. This is our system now. This is what we have been talking about. Let me put this tube in here and call this the system. Now, when this changes, when it crystallizes, the entropy change is delta S. I've written that on the thing. Delta SS, delta S, little s for the system. But when this process occurred, we remember that heat was given out to the thermal surroundings. Here are the thermal surroundings. They were cold originally. The molecules, these little arrows representing the molecules, were moving very little. Heat was given out and they move more. This is more disorder, more entropy of the thermal surroundings. Heat Q is given out. The entropy of the thermal surroundings increases by an amount Q over T, which we've seen is the measure of entropy. Now, we therefore have two entropy changes, delta S of the system and Q over T of the thermal surroundings. That is our universe. Let's put it in a box so that we isolate it from all other changes. This is now a closed system, and the total entropy increase in the universe is delta S of the system plus Q over T of the thermal surroundings. And all that matters is that the sum of those shall be positive, that the total entropy increase of the universe shall be positive. And it doesn't matter which way, both can increase, one can increase, the other decrease, but not both decrease. There are many combinations of these two terms which make spontaneous changes possible. Let me show you one which is the exact opposite of the one we've just seen. The one we've just seen, remember, represented an increase in order, but heat was given out. Here's the opposite. Here is some ammonium nitrate. And when this dissolves in water, it takes in heat. Complete opposite. The entropy of the thermal surroundings will decrease. If you look at the temperature at the moment of this, it's the temperature of the room, which is 20 degrees centigrade, the thermometer showing 20 degrees centigrade. And now I'm going to pour the water into that, and you should see the thermometer change the temperature as I pour it in. There, you see it falling rapidly. It's fallen to 5 degrees, so to 15, 10, 5, and it will in fact go below naught. Heat is being taken in, so the entropy of the thermal surroundings is decreasing, but that's all right because the entropy of the system is increasing as the ammonium nitrate dissolves and the molecules become spread out and more random. The same considerations apply to all sorts of changes: polymerization, burning, combustion, decomposition of substances, and so forth. And they apply also to mechanical systems. Although mechanical systems seem a little bit different at first sight. If this is a perfectly good ping pong ball and bounces bounces as a perfectly elastic one, which it won't and which no ball does, then no change occurs. If it just goes up and down like this and doesn't run down, then this is just a periodic process. There's no permanent change. But if it runs down, as it does, rather slowly or more quickly in the case of a very inelastic lead ball, then how to explain this in terms of entropy? Well, firstly, there is no difference whatever in entropy between that and that. The height doesn't affect the entropy. Where is the entropy increase? Well, of course, the entropy increase occurs when the ball hits the bench. Let me show you what I mean in terms with this block. When the block is up here, it has the same entropy as when it's down here, but as it falls, it gains kinetic energy. You see the molecules have ordered energy like this. Molecules have ordered energy as they fall down like this. But then as soon as it hits the bench, that ordered energy becomes disordered. The molecules are moving all over the place like this. So we have the entropy increase represented in molecular form from that ordered kinetic energy to that disordered kinetic energy or heat. And all our mechanical changes of this kind can be explained in the conversion of ordered mechanical energy into heat. This happens all the time as pendulums gradually run down and we have to wind up our clock again, as springs gradually run down, as we run down, as everything runs down, the ordered motion becomes disordered motion of heat. And this represents the increase in entropy of the whole universe. Well, we've been able to explain then processes of all kinds in terms of entropy increase. And as long as we remember that it is the total entropy of the whole universe which is increasing, then it doesn't matter whether the system gives out heat or takes in heat, or whether the system becomes more ordered or less ordered, providing both the system and the thermal surroundings become more disordered, acquire more entropy together, so that the entropy of the universe increases. This means that the change can occur spontaneously, and indeed will occur spontaneously. You may ask, then, having accepted this, say this is all very interesting, but how is it, how can it be that things are so unidirectional? How is it that entropy always increases with time? Well, science doesn't normally answer the question how, it's more concerned with why. But if it had to answer this question, if it had to decide why entropy increased with time, it would have to say, because time goes forwards. And you would say, well, that's a pretty useless sort of answer anyway. But if you think about it, it's an interesting answer, because in fact this enables us to give an arrow to time. The term arrow of time was first used by Eddington, and it's an interesting idea. The direction which we can give to time provided by this unidirectional second law, which says that entropy is always increasing. Suppose, and this is now a familiar thing that we think about in this day and age, suppose we were transported to another part of the universe, and we suddenly started being worried about the direction of time, as to whether we were going to see our heirs or our ancestors when we got back. How could we tell which way time was going? Well, it's really quite easy. All we would have to do is look at something which happened spontaneously and decide whether the entropy increased or decreased. Now, I'd like to show you an experiment with time going backwards, but this, unfortunately, in this universe is not possible, because the second law of thermodynamics forbids it. But one can illustrate the point rather nicely by moving film. We can make film go backwards or forwards, and because this is such a good illustration of the direction of time, you cannot tell whether the film is going backwards or forwards unless there's an entropy change in what is being filmed. Now, I'd like to illustrate this to you by showing you a little bit of film which we've made, and the first part of this film shows my two boys behaving much more reversibly and less chaotically and less disorderly, if I may use the word, than is their usual custom. And I'm not going to tell you whether this film is going backwards or forwards, because, and since there is no entropy change, or at least Andrew here is trying not to increase his entropy or the entropy of the swing or anything else, it's very difficult to tell whether the film is going backwards or forwards, whether time is going backwards or forwards. Here are those pendulums which we saw before. And unless we watch them long enough so that something runs down or runs up, an entropy change, then we can't tell whether the film is going backwards or forwards. Here I am moving bricks around and trying to keep myself as near to equilibrium as I possibly can by doing it slowly, not dissipating any energy as random heat. Here one is doing a rather useless thing. We're mixing something which is already mixed, and we're getting nowhere at all, and therefore you can't, there's no change in entropy, and you can't tell what is happening. And here I'm very, very carefully drinking a cup of tea in a reversible fashion, and since I always stir my tea after I've drunk it, you can't tell which way the film is going. Well, that part of the film was isoentropic. There were no entropy changes, and so it was very difficult to see which way it was going. It was in fact going the same way as this part of the film, where entropy does change quite clearly. Here is the sugar going back into the sugar bowl, which we talked about before. It can only happen in the world of the film, and all of these changes leave you in no doubt. You see, here is unmixing occurring spontaneously. They leave you in no doubt about the direction of time. Entropy is all the time decreasing. As a matter of fact, the first part of the film was also running backwards. But since there were no entropy changes, you couldn't tell. There is that unmixing. And here is a peculiar sort of process, which we don't see every day, where this little ball gathers up the random motion of the molecules, and this one does the same. It gathers the random motion of the molecules in the bench and in the ball, gets them all ordered so that those molecules are, instead of moving in random directions all over the place, begin to move in one direction, work themselves up, and jump upwards into my hand. Here is a chemical change going reverse, with a decrease in entropy, the unlighting of a match as the molecules gather themselves together from the air. And finally, the nursery example. How nice it would be if we could just from time to time reverse the direction of time and the direction of the second law, so we could just do that in the nursery. Well, in every part of our universe where suitable experiments can be made, time does appear to go forward, in the sense that the total entropy now is greater than in the past and will presumably be greater still in the future. The second law works forwards as we have described it. Insofar as the universe is the sum of these parts, and is itself a closed system of constant energy, volume, and mass, it must exhibit this irreversible trend towards total chaos and a heat death of timeless equilibrium. But it would be premature to lose very much sleep over this. Cosmological theories are highly speculative at present, and science has learned to view long extrapolations of this kind with caution. It's a very long step from the disorder of molecular motion to the chaos of the cosmos.